Rollups feel cheaper and faster, but the real reason has nothing to do with execution. The real cost of a rollup is the data it posts to Ethereum. And once you understand how that data is compressed, the economics of layer 2s finally make sense. Today, we're breaking down gas compression, what rollups actually pay for, how they shrink their data footprint, why compression is the main competitive battleground for every layer 2, and how EIP 4844 changed the entire structure. By the end of this episode, you'll understand why compression is the engine that makes rollups affordable. You see, rollups pay for data. Every time a rollup posts a batch to Ethereum, it pays for the bytes it stores on the chain. That is the bill and the bottleneck. So that's why compression exists. Without compression, rollups would be expensive to use. With compression, they can fit thousands of transactions into a small data footprint and spread the cost across everyone on the batch. A rollup compresses far more than what most people realized. It is not just shrinking transactions, it is shrinking every part of the batch that costs money on Ethereum. Start with the basics. A transaction contains addresses, signatures, call data, and metadata. All of that takes space. A rollup strips out repetition, shortens fields, aggregates signatures, and encodes the data in a way that takes many fewer bytes. But it goes deeper. Rollups also compress state diffs. Instead of posting the full before and after state, they post only the minimum changes. They compress repeated values. They compress zeros. They compress patterns that appear across many transactions. The goal is simple. Fit as many transactions as possible into the smallest possible footprint. Because the smaller the footprint, the cheaper the batch. And the cheaper the batch, the cheaper the chain feels. Before EIP 4844, rollups posted their data as calldata. Calldata is expensive because it lives permanently on the execution layer. It competes with every other transaction on Ethereum. And when the network gets busy, calldata becomes more expensive. That made rollup fees volatile and unpredictable. EIP 4844 changed everything. It shipped on March 13, 2024 as part of the DEPCON upgrade. This upgrade introduced a new transaction type called blob carrying transaction. Instead of paying for a permanent call data storage, rollups can attach large chunks called blobs that consensus clients verify once and prune after about 18 days. This creates a separate, much cheaper data market that sits alongside the normal gas market. At launch, each Ethereum block could include between 0 and 6 blobs, with a target of 3. Each blob consists of 128 kilobytes of data. Rollups pay for the entire blob, whether they fill it or not. The data is stored using KZG commitments, which let the network verify availability without forcing every node to store the full blob forever. I apologize. This is why blobs are cheaper. They are temporary, verifiable, and designed specifically for rollups. Blobs also have their own market. They use an EIP 1559 style pricing curve with a base fee that rises or falls depending on blob usage in the previous block. All blob base fees are burned. This isolates rollups from execution layer congestion and gives them predictable data availability pricing. That was impossible with calldata. The impact was immediate. When Proto Danksharding shipped in March 2024, median fees on Arbitrum, Optimism, Base, and zk-sync collapsed from tens of cents to fractions of a cent overnight. Rollups did not become free, but they became economically viable at a scale for the first time. And Ethereum has continued expanding block capacity. The Pectra upgrade in May 2025 doubled blob throughput. The Fusaka upgrade in December 2025 introduced PeerDAS, improving data availability sampling. 2 follow-up blob parameter-only forks pushed the per block target from 3 blobs to 14, and maximums from 6 to 21. The long-term goal is 128 blobs per block under full Danksharding. Compression multiplies all of this. If a rollup can shrink its data by half, it uses half as many blobs. If it can shrink 80%, it uses a fraction of a blob. This is why compression is not a side feature, but it is the economic engine of every rollup. Compression is not just one trick, but a stack of techniques working together. Rollups use dictionary compression to replace repeated patterns with short references. They use address shortening to avoid posting full 20-byte addresses when a smaller representation will do, which means they aggregate signatures so that dozens of signatures can be represented as one. They pack transactions tightly so there is no wasted space. They encode state diffs so that the only minimal changes are posted. They use zero encoding to compress long runs of empty values. And some rollups hold custom algorithms tuned to their VM or execution model. Every improvement shrinks the batch. Every shrink lowers the cost. This is why rollup teams invest heavily in compression research. It's not cosmetic, but it is the core of their economics. Users never see compression directly, but they do feel the results. They feel it when a swap costs cents instead of dollars. They feel it when a game runs smoothly because the chain can handle more throughput. They feel it when a bridge finalizes quickly because the batch is small enough to post efficiently. Compression is the invisible engine behind the user experience. It determines how many transactions fit into a batch. It determines how many batches are posted. It determines how predictable fees are. It determines how the chain feels. Rollups are not competing on raw throughput. They're competing on data efficiency. The rollup that compresses the best delivers the best experience. So, every major rollup is now a compression company. Arbitrum focuses on calldata, encoding, and signature aggregation. Optimism focuses on batch packing and blob efficiency. Base focuses on OP stack improvements and shared infrastructure. ZK Sync and StarkNet focus on proof compression and state diff encoding. They're all solving the same problem from different angles. How do you fit more activity into fewer bytes? How do you reduce the cost of posting to Ethereum? How do you make the chain feel cheaper without sacrificing security? This is the new battleground. Not branding, hype, but compression. The rollup that compresses the best wins the economics and wins the users. Compression is moving quickly. Better algorithms, better batching, better blob markets, better proof systems. Costs fail as compression improves. This is the closest thing Ethereum has to a Moore style curve. Rollups get cheaper every cycle. And the next generation of rollups will compete almost entirely on data efficiency. In the next episode, we take this out of theory and into practice with a full UX walkthrough. How a transaction moves into a rollup, how the sequencer handles it, how the batch is built, and how it lands on Ethereum. So stay locked.